All right. Thank you for about a minute late. How's it going? Good? Yeah? All right, that's good. Thanksgiving's around the corner. Some exams coming up. So Tuesday we have exam number 2. You can bring how many pieces of paper? 2, right? Front and back. Yeah, please feel free to write whatever you like, okay, on them. And now, essentially, the idea is to bring in, the sheet from your previous exam. You might modify it slightly, and then for this one, you should have another sheet. Okay. Any questions? All right. Okay, what do you all think about? Yes, go ahead.
What sessions are going to be on the next exam?
So through session 20, which is on Tuesday, and then I guess I saw in the group you people had some ideas of what maybe they go back to, but around session 9 or so, I guess, right? Not 4. So that's, but you got, like, free body diagrams do not disappear, right? Normal stress does not disappear. Shear strength does not disappear. Shear stress does not disappear, right? So it's still short. Yes.
It feels inconsistent. Is it possible to make an announcement maybe or anything so we know exactly till when from when?
I will send out an announcement that says you can bring 2 pieces of paper and it's exam number 2 and it covers up to the last Tuesday section.
From where it starts? Because
Session 1 then. Session 1 to session 20. Okay? Yeah. So, all right, so here we go. We have an opportunity to cover, all right, another aspect of 2D stress and strain. Today we're going to cover plane strain. Okay. Now, we're going to break this into 3 parts. We're going to have a little introduction on the plane strain and transformations, right? And thinking about how we can use the transformation equations that we've used before, okay? And how they're maybe a little bit different when we think about plane strain, and what the condition, which is slightly fictional, might be to thinking about plane strain and plane stress being equivalent. We'll talk about more circle, okay, and how to use it with strain instead of stress. And so the big thing that we'll see here is that we have not a tau, but we're going to have gamma xy over 2. So this is a little bit confusing, okay? So this is actually, yep, that is a typo that I took care of later, but not here. Okay, we have, this should be gamma xy over 2. Okay. And then, of course, we'll talk about how this is applicable to actual structures. Okay. And in particular, we'll cover how we use this with strain gauges. It's hard to know exactly what stress might be in a structure. Okay? And that, if you've taken a look online, maybe you've seen some things like stressing photoelasticity. Okay? And so sometimes you can get an idea of what the distribution of stress and strain might be in an object through image processing techniques. Another one is called digital image correlation. Okay? But the classic method that we use to be able to discuss or be able to analyze what the strain and stress might be is through what we call strain. Okay. All right. So plane strain. before we discuss the simplified nature of plane strain, we realize that if we're describing strain, we have 6 components. Just like we had 6 components of stress, right? We can have 6 components of strain. Okay, epsilon x, epsilon y, epsilon z, gamma xy, gamma xz, gamma yz. Okay, but then just like we do with plane stress, where we say, okay, we're only really interested in plane stress, right? We're only interested in 3 components of stress, okay, for a plane, right? We're interested in the sigma x, the sigma y, and the shear stress. Okay. In this case, the 3 components that we're going to be interested in are the gamma xy and the epsilon x and the epsilon y. But what are we really doing? What we're saying here is that there's no strain in the direction normal to the plane of interest. Okay? So what we're saying is that the strain, for example, the epsilon z, okay, that's going to be 0. We're saying that the strains like gamma xz and gamma yz, right, where we say that second subscript has a component in the normal direction, we're saying those are 0 as well. So typically, to think about this, we're looking at thick plates. That's kind of the image that we keep in our mind. Okay, so that what's happening, there's not going to be much, there's not strain in that z direction. Okay, it's really thick in that direction. And we are focusing on motion or deformation, right? That is only in the plane, right? So like the 2D plane. So xy is the common plane that we use for 2D. Right? So if you're thinking about the strains, right? It's like, okay, epsilon x, we know what epsilon x is, right? It's the delta in the x direction, right, divided by the width, or that length in the x direction. Okay? And if you're thinking about the delta y, or the epsilon y, right? You're thinking, okay, how much is it changing in the vertical direction from what we got? The one that is, of course, a little bit more confusing and a little bit more stressful is usually the shear strain. Okay, so we have a gamma xy, and we've talked about this in the past. Okay, we've mentioned how we can think about the strain, right? The gamma xy strain, right? And you can think of it as sometimes, and we'll show some pictures before, if this bottom blue surface were on this bottom piece, right? You can think of it, oh, how much deformation, okay, do I have of the top plate versus the bottom plate, and what is the angle that's formed here, all right? Or if you think I have some original orthogonal or right angle right here, I can think about, okay, how much has the rectangle or the square changed its angle in this corner, and then I take 90 degrees minus that theta. And of course, we report this in radians. And this is usually, for our intents and purposes, very small numbers. You'll see as we do these strains, we're often, and even, right, these strains, these epsilon x and epsilon y's, what we're going to be talking about is stuff on the order of 10 to the minus 6. Which is maybe not too surprising, because when we talk about stresses, we're talking 10 to the 6, right? We're talking megapascals, so now we're 10 to the minus 6 here, right? And, you know, for Hooke's law, for axial loading, right, ignoring, the Poisson ratio effect, right? We just say sigma is equal to E epsilon. Okay, and the elastic moduli that we have are 10 to the 9 often, plus. Okay, any questions up to this point? Okay. Now, when we think about these two cases, the plane stress and the plane strain, we might think, when might they be the same? When might they be equivalent? And when we do that, it's a little bit confusing because we've got something that might be really thin, all right, which is what we typically think about with plane stress, right? The prime example that we use for plane stress are thin-walled pressure vessels, right? That's one of the examples we use. Okay, and what we've said, right, is that the stress in the z direction is very small. Okay, we've typically said that we're going to assume it's 0. In this case, we've got something that's very thick. So when can these two cases be the same? And it's when the Poisson ratio is equal to 0. Now, is that real? Is the Poisson ratio going to be 0? No. Okay, not really, right? Okay, and just as a refresher, what are we saying here? We're saying that if you're thinking about epsilon z, and you have stresses, right, in x, y, and z, and these are normal stresses, and we can think about the effect of the stresses in x and y on the z, right? And so if there's a non-negative or non-zero, Poisson ratio, then there can be some influence on epsilon z, okay? Assuming that sigma z is 0. And that's not what we want in the case of plane strain. In plane strain, what we're saying is that epsilon z is supposed to be equal to 0. So that's kind of the fictitious condition, right, that we can think of when these two are equivalent. Nonetheless, okay, we usually make some simplifications, and we will kind of think, yeah, okay, so the Poisson ratio is not really 0, but if it's a really big plate and I put a measuring device, what we call a strain gauge or rosette, we'll talk about this a little bit, on the top of this surface, okay, we're going to say, the strain normal, okay, to the surface. So I've got a surface, and I slap my strain gauge on top of it. We're going to say that the epsilon z is going to be negligible in that particular case. Okay. At least for our intents and purposes for doing the transformations that we're going to do later. Okay, so now let's review. I think these slides are from the past, maybe with some slight embellishments, to talk about normal strain and shear strain in a little bit more detail. Okay, so right, you can draw this element, okay, that has some small areas for some type of cube, okay, and we can draw out the 2D profile of the XY plane, okay, and this is where we were saying, all right, same thing that we just showed before. We have a dy dx, okay, and we can think about how epsilon x and epsilon y are going to be influenced, okay, here. And in this case, we're saying, oh, if there's some delta x, right, that's going to give us epsilon xx, all right, which we simplify as being just epsilon x. And if there's some strain off in the y direction, right, we can think about it as epsilon yy, which is the same as epsilon y, right? So this is pretty straightforward, and we've kind of covered this. Shear strain, we've kind of covered this as well, but I think it's just, again, a good reminder in terms of what it looks like. Okay, so once again, we have our nice little cube, all right, with our nice coordinate systems, or our coordinate axes, all right, and we can look at the 2D profile in the XY plane, and like I was hinting at before, what we're talking about in some cases is we keep the bottom flat and we shear, okay, it is a shear strain, but we shear the top, okay, and then what we're looking at is this displacement here, and this displacement here, and we're looking at the angle this forms, okay, and that's the shear strain, okay, and often, what, like we were talking about before, if this, to be very clear or to be more precise, this bottom surface actually comes off for an element in pure shear. And so we end up thinking about 90 degrees minus this angle in here. But in this case, we can say, oh, if I want to know this angle for gamma, it's going to be this delta over the dy, right? And when you take fluids, you know that that's how you calculate you're thinking about shear stress in liquids, okay, based on slipping between plates and this angle that can form, okay? So that's a way that we write shear strain, and we can think of gamma xy. And again, to be more like purist, what you would see here is you're actually thinking about the summation of this angle below and above, and it's going to be 90 degrees minus the interior angle of this four-sided sheared piece. Okay. Okay. Now, here are the general equations. You probably want to write them down for the final exam, not for Tuesday. Okay, because what we're covering today is not on Tuesday's exam. Okay, and if you want to see the derivations, you can take a look at Hitler's book, or you can click on this link, and you can see the derivations for these transformation equations. What do we notice? We notice, okay, that they're similar to the equations that we had for transformations on stresses. Okay? And we'll get into how they're a little bit different. We also know that we can figure out the angle at which you would have what we call principal strains. And we can figure out what those principal strains are, right? And one way to figure out local maxima or local minima, all right, is that you have a derivative of this strain, okay, that you have. Maybe you could start with your epsilon x prime, take that derivative with respect to theta, and figure out where it's an absolute or a local minima or local maxima, and you can figure out, okay, that's the angle that needs to be rotated, okay, to get this condition, and because you're going to set that equal to 0, right? So d epsilon x prime with respect to the derivative of epsilon x prime with respect to theta, you're going to set that equal to 0, and then you can figure out what the angle should be, and then you can plug that back in to the epsilon x prime and figure out what your epsilon 1, 2 would be, and these are going to be the principal strains. Okay. Similarly, we can figure out when we're going to max out our shear strain, and by looking at the angle, okay, so looking at the equation here for shear strain, and then figuring out what the angle would be, and then plugging that back into the equation, and you can figure out what the gamma max in plane shear strain will be. These equations have an interesting property, though, right? What you see here is we typically wrote tau. When we're doing the shear stresses, we wrote tau x prime y prime is equal to this, a quantity, right, sigma x minus sigma y, or something over 2. And now there's another quantity, okay, where this is not just tau, but it's gamma x prime y prime divided by 2. And so this factor of 2 comes into the equations, all right, and it comes out of the algebra. And in this case, there's not a factor of 2, right? Okay, this is like flipped. So if you had been doing the tau before, you might have had a factor of 2 here. Okay, but these equations these are accurate. It's circling, like sometimes it was confusing because I circled a nothingness. Okay, it's circling that there's no nothing. There's circling that there's nothing there. All right, and if you look at the substitutions, all right, once again, we're thinking about tau xy as being you're having these parallel equivalencies. All right, so tau xy goes to gamma xy over 2. Right, sigma x goes to epsilon x, sigma y goes to epsilon y, and these transform versions do similar. Okay. Any questions on this? Okay.
What is gamma?
Gamma is shear strain. And yeah, gamma is, just to be clear, gamma is this Greek letter right here that you're seeing. And this Greek letter is epsilon. Yes, gamma is the shear strain. Yeah. Okay. And it's, when you have the clue there, right, is that it's shear when you have 2 subscripts that are not the same. Right? You have xy as a subscript, right? And it's the same thing, right? Those subscripts, the first subscript, that's the face it's acting on, right? And the second subscript is the direction it's acting. Yes, Kevin.
Could you go over one more time the difference between theta sub p and theta sub s?
Oh, yeah. So theta sub p, right, is the angle we have to rotate to get to the state of principal strains. So principal strains are just like principal stresses, where it's a state, we've rotated to that state where we have only epsilon x and epsilon y, or epsilon x prime and epsilon y prime, right? We only have normal strains. There's no shear strain, okay? And just like we had in the state of maximum in-plane shear stress, when we have maximum in-plane shear strain, we have maximum shear stress, right? And that does not mean that the normal strains are 0, right? When you have maximum in-plane shear stress or maximum in-plane shear strain, okay, you can still have normal stresses. When we have principal stresses, right, which is when we have the normal stresses being maximum, or we have principal strains where we have the normal strain, one of those normal strains being a maximum, okay, that means that there will be no shear strain or no shear stress. Okay, that's the difference. That's a big difference, right? And remember, Moore's circle spits that out to us, right? You're like, oh, Moore's circle is on a tau sigma axis, and we're going to cover this in a segment, right? Or Moore's circle for strain is going to be on a epsilon gamma over 2 axes, set of axes, right? So you can get to the state, when you draw the circle, right, you can get to a state for any circle where you have 2 points on the sigma axis or the epsilon axis, which means that the shear is 0 in those situations, right? But unless Moore's circle is centered on the origin, you can't get a state of pure shear, right? Because in order to have pure shear, that means that you've got to be on the tau, or the gamma xy over 2 axis. Okay? Maybe that was a lengthy explanation, but hopefully that's helpful. All right. So now let's spend a few minutes, all right, going about, all right, looking at an example. What is the state of strain for an element rotated 45 degrees from a condition of uniaxial strain? Okay, so uniaxial strain, right? That's like uniaxial stress or uniaxial loading. Okay, so we've got a strain in one direction, okay? And these are the same exact equations that we just had. What do? We say, okay, the element is rotated 45 degrees. That's not rotation of we're talking about the element, right? On Moore's circle, that would be a 90-degree rotation, but we'll do that in a minute. So it's kind of just plug and chug, all right? You take a look at these equations, you plug in theta equals 45 degrees, recognize that's 2 theta, so it's going to be 90 degrees. Recognize that there's in uniaxial strain, in this case, we have 0 shear strain, and we have 0 epsilon y. Epsilon y is equal to 0 as well. Okay, so we just get rid of those other terms, and in this case, the new epsilon x prime is going to be epsilon x over 2. We go down to epsilon y prime, okay, and we plug it in here, and we also get that it's going to be epsilon x over 2. Okay. And we look at gamma x y prime, remembering that there has to be a factor of 2 over here, and we can write out that it's just going to be negative epsilon x over 2. And then we have the 2 and the 2, and so we can say that gamma x prime y prime is equal to minus epsilon x.
I have a question.
Yes?
Why are we solving for gamma, which is the shear strength, if the question was correct?
Okay, so what we're saying in this state, the initial state of stress was this, essentially, right? Or sorry, initial state of strain was this. Okay, we've got just being extended out in x. Okay, and we've got a dx, and we can divide by, or we've got a delta x, and we can divide by dx, right? And that will give us our epsilon x. Right? That's what this state of strain is describing. But then, just like we do in Moore's circle, we said we're going to rotate the element 45 degrees. Okay, so when we rotate the element 45 degrees, now we're interested in the state of strain that is for this. Oops, this mouse doesn't work. Maybe it does, maybe it doesn't. Okay, not work. So it's this case, right? Right. This is the elements at the same location, just like we do with stresses in the past, or we've done stresses in the past. But now we're looking at it rotated 45 degrees, so we have a new x prime, y prime coordinate system. Okay, and we have to use all 3 of these equations to figure out what the epsilon x prime is, what the epsilon y prime is, and what the the gamma x prime y prime would be on that face. Okay, so we did the math first, but now let's draw what it looks like. Okay, and it looks something like this: a distorted element. Okay, because remember epsilon x prime and epsilon y prime, they both are positive, so let's say it expands out in both the x prime and the y prime direction slightly, and then we have a negative shear stress, or negative, I keep saying the wrong thing, the negative shear strain, okay? And so this is actually a little bit, what's interesting here, right, is remember in the previous examples, when we drew the shear strain, we drew the new one with the distorted box inside the original box, okay? Because the shear strain was positive. But when the shear strain is negative, what happens is the green went outside the original black box, okay? Because the shear strain is negative in this case. So these values, right here and here, assuming that this is nicely evenly spaced, what would you say? What is this angle here and what is this angle here? Based on what you see here. Anyone? Yes, Paul. Say that again? Okay, so we didn't specify, I know where you're going, right? We didn't actually specify what epsilon x is, right? So I need it in terms of epsilon x, right? But I calculated it. I calculated out what gamma x prime y prime is, okay? So remember, it's going to be the pi over 2 minus this interior angle, okay? Or this interior angle here, right? And each one of these, the way we've drawn it, each one of these will be half the shear strength. Okay, so each one of these is going to end up having an angle relative to this black box of epsilon x over 2. Okay, just like this. Did that make sense? Maybe, kind of, sort of. All right. The way we've drawn it, these are actually positive. The way it's drawn because it's opened up this way. All right. So these are actually like positive, but this is describing the shear strain. Okay, and it's half the shear strain. Because if we go all the way back to here, remember, we said if I keep the flat bottom flat, then it's just that angle. But if I pump it up, right, if I let it deform purely, then I have these two angles, and it's the summation. The gamma is the summation of these two angles outside. Okay, and that's why, and then if it's symmetric, if alpha is equal to beta in this case, then it's going to be, they're going to be equal to each other, so it's going to be half of the shear strain. Okay. It's a little confusing, all right? That's why we're trying to clarify things a little bit here with these examples, or with this example. Other questions on this? Are you raising your hand, Chris, or you're just stretching? Other questions? Yes, Kevin.
So to write up the final answer, to describe the state of strain, would an acceptable answer comprise of like strain y prime, strain x prime, and just putting it symbolically like that? Or like how would we?
Yeah,
write
so, yeah, I mean, for these, if I don't say use Moore's circle, just use the equations, right? I don't like, personally, these, how do you say it? These plane strain transformations are a little less, they're a little unnerving to me compared to the plane stress transformations, okay? Okay. But you don't need to worry about this for Tuesday. Okay. Example 2. Now we're saying we've got normal strains of epsilon x and epsilon y, all right? Okay? And now what we're saying is just rotate by some theta and tell us what is the new state of stress. Okay? What is the state of strain for an element rotated theta when you have epsilon x and epsilon y, as you see here. So in this case, you plug in these values, just like you see them, and now we can write out the new state of strain. Okay? And if we think about it, the original might have looked something like this with x, y coming out. Okay? And now we've deformed things where we have epsilon x, okay? We have epsilon y, okay? And now we're rotating, and the new element, okay, might be rotated like that, and the new strain element might look something like that, okay? And now we're saying that we have a new epsilon x prime, and we have a new epsilon y prime, and we also have, right, these two here that are going to be the gamma x prime y prime over 2. Okay. So we've now gotten a little bit comfortable, hopefully, with using these transformation equations. Now, do you remember this slide? This is from session 9. This is a long time ago. Okay? And while exam 2, right, technically you can go all the way back to session number 1, right? I'm not going to limit anything. But session 9 is kind of where I think, practically speaking, you might want to start. We talked about Hooke's law for pure shear. And we introduced G. Right? And what is G? Shear modulus, right? And physically, what is G? When we're talking about relating shear strain and shear stress, what is G? Okay, yeah, okay, it's the ratio. Yes, good, good. All right. Yes, Federico. I couldn't quite make that out. What did you say? Yeah, or I mean, like, maybe a more philosophical question. What are G and E really? Okay, yeah, so they are, we can think of them as material spring constants, right? Normally spring constants are relating force to displacement, right? Or torsion to angular displacement, right? Or, sorry, torque to angular displacement. So yes, they're kind of like material spring constants. And in fact, when you look at different models, like if you do simulation stuff, you'll see that they use springs, dash pots, okay, to define models for materials as well. So yeah, there's spring constants. There's like, and G is kind of like, and E is kind of like, how much does the material resist deformation, okay, when you apply a stress? The higher the E, the higher the G, right, the less deformation, the less shear strain, right, the less, in E, the less normal strain you're going to have. For G, the less shear strain you're going to have. And G is really important when we talk about shafts, okay, right, because that's what we use to relate the angle of twist or the shear strain and the shear stress to each other. And when we have twisted shafts. Okay. All right. So when we have shear modulus, we discussed that there was this interesting relationship. Remember this? And I said, one day in the future, we will define, or we will derive how we got E over 2 times 1 plus 0. Okay? Today is the day. All right? So, before we do it though, just as a recollection, right? And this is, just like we have the stress strain curves, we can have shear stress, shear strain curves. All right, let's go. So for this derivation, we start with an element in pure shear. And it looks something like this. Then we say, let's rotate the element by 45 degrees. So on Moore's circle, okay, in the old good days, when we had plane stress. Now remember we were saying, hey, what is going on? It's not exactly a great idea to relate and say that plane stress and plane strain are equal, okay? We're gonna forget about that just for a second, okay? So this is Moore's circle, and we have our sigma 1, sigma 2, and our sigma 3, okay? And we've rotated by 45 degrees, right? And how do we get that? Because this is pure shear, so we started here and here, and then we rotated 90 degrees on Moore's circle, so we got to here and here. Okay? And the radius of that Moore's circle is just the tau xy. So now we've got this nice, interesting relationship where we have a sigma 1 coming out, and we have a sigma 2 going in, and they're equal and opposite to each other. We know from our constitutive relationships, all right, in the past, that epsilon x can be given as 1 over e, all right, times sigma x, or this quantity minus the Poisson ratio times the summation of the normal stresses, okay? And we're going to then say, okay, this is what epsilon 1 is equal to, right? We just plug in our sigma x, all right, in this new state, all right? Our new state says that it's tau xy here, and it says that the sigma 2 is the minus tau xy, and we have this new right here. And so now we have epsilon 1 is equal to this relationship times 1 plus mu. The principal strain, okay, can be derived as the following, okay, or can be written as the following. And this is from previous slides that we just had, okay? And so now we can say that epsilon 1, okay, is going to be, for this, if you plug in, all right, these values, all right, that we had previously, where epsilon x, all right, was 0, and epsilon y was 0 because we were in pure strain, okay, then epsilon 1 is just going to be the square root of this term over here. Okay? And we also know for a case, this is pure shear, remember? Pure shear, we said for pure shear that tau xy is equal to g times gamma xy. Okay? So now we've got an expression for epsilon 1 and the gamma xy. We've got a relationship between tau and gamma xy. Right? And we have a relationship for epsilon 1. So we have this equation, this equation, this equation. We start putting them together, and what do we get? We get that g is equal to e over 2 times 1 plus 3. Okay? And that's the relationship that goes between elastic modulus and shear modulus that we've been using already. And that's how it's derived, or one way you can derive it. Okay? Now, this relationship is very important, and it's also good to know when it's valid. Right? This is valid for what we call isotropic materials. Okay? Isotropic materials that are linearly elastic. So that means that, you know, if I pull in any direction, normally, right, it's going to have a relationship with the elastic modulus. Okay. Good. Let's spend a few minutes, all right, and take a look at question 1. Okay, it's giving us the state of strain, okay, where we have epsilon x equals some epsilon, epsilon y equals some minus epsilon, okay, and then we're rotating 45 degrees from this condition, okay. And the question is, was the original state a state of principal strain? And is the new rotated state a state of max in-plane shear? Okay. Remember, we just did an example, okay, where we had pure shear, right? A case of pure shear, which meant that we only had, you can rotate by 45 degrees and get a state where you have a normal stress, positive, a normal strain, positive, right? And the other orthogonal one, the normal strain, normal stress are negative, right? So that should give you some idea here. So spend a few minutes on this, okay? And if you wanna, so if you're working on it and you wanna, the thing you wanna be looking at, or the most similar example to what we just, the most similar example to sorry. All right, this is kind of the most similar example right here. Okay, so what we're discussing here. Yes.
You rotate the element by 45 degrees to get the relationship between Young's modulus and shear modulus. Is there a reason why they chose 45 degrees to describe the rotation? It seems like arbitrary.
The reason we did it, well, we also started with an element that says pure shear, right? Okay. The reason we did that is because G, right? Another use of G is to describe relationship thinking about you're not thinking about straight.
Right. But so how is that 45 degrees? Is it just 45 degrees is where there's typically?
Well, so 45, the reason we 45 degrees from pure shear, right? To go from maximum shear stress to I go from maximum shear strain to principal stress. I go 45 degrees on the elements right? And if you think about it, if you're trying to relate elastic modulus to shear, right? Elastic modulus is all about normal stresses, the normal strains, right? Whereas G is all about shear stresses and shear stresses. So we pick a scenario where we could go between the two just by rotating 45 degrees.
And 45 degrees is optimal because we know what the material behaves at 45 degrees.
Yeah, well, you know from the equations, right? I know that when you go 45 degrees, you're going to go from a state of pure from maximum shear stress to principal stress. Right? So the element was protein yeah. Okay. Are people working on this? They're done? Yeah, good. Thumbs up, thumbs up, thumbs up. No? Okay. I've got a wait a couple seconds. Other questions?
We finished.
Alright. Yeah. Alright, good. Good, good. Good. Okay.
I don't fail.
Okay, can we move? Okay, we're gonna move because we need to get going to some of the other stuff, okay? All right. So, okay. Now, we're gonna discuss Mohr's circle. So, as we've already kind of suggested, all right, we have some very interesting parallels between the transformation equations that we've seen for Mohr's circle with stresses, with plane stresses, and the transformation equations for plane strains. And these are the transformation equations for plane stress. These are the ones for plane strain. And when we do this, what we see, right? Remember, Mohr's circle, at its heart, we're describing the center of the circle, right? So there's a sigma average, which tells us the x component. The lack of a y or a vertical component, right, means that it's 0 and it's going to be on the sigma axis, right? And we have our r, which is the radius, right? And so this equation is what you find for a circle. Now, for our transformation equations, okay, with plane strain, we have very similar relationships. But tau squared x prime y prime is just tau squared x prime y prime, whereas gamma x prime y prime has this factor of 2 underneath it. Okay. So when you look at plots sometimes, right, you convert them between units, right? And it's like, oh, is that in meters? Is it in millimeters? Whatever, right? Or sometimes people will say, oh, this is in decibels or something like that. And you got like this 20 log 10 thing going on, right? It's not much different here. What we're saying is that we've got a factor of 2 inside here, and we're just going to make that our y-axis. And once again, to make the rotation of an element in a counterclockwise direction to be the same counterclockwise direction on Moore's circle, we're going to define that shear strain to be positive going down. Okay. So we have the center of the circle, right, as given by the average of the normal strains. We have our epsilon x and our gamma xy over 2, right, as being a coordinate on the Moore circle. And we can figure out where this would intersect, where it would intersect the epsilon axis, right, and figure out what that distance is. And we can figure out then what r is that way, if we like, right, because it's going to, you can use the Pythagorean theorem again for this and this side, and that's what you get here. Okay. Any questions on this? So here's another question. Okay. Now, if we have a Moore circle, okay, and what is the epsilon z in this case? Okay. Like for this next one. So the first question here is asking us to look at what the largest principal strain is. So when you have largest principal strain, how many more circles do you typically have to draw when you're looking at principal stresses? When you want the maximum principal stress? How many, and it's 2. You need 2? 2 more? Okay. So typically, just 1. Alright, typically you only need, if you're looking at the maximum one, right, you're going to draw, okay, so in this, whoops, typically, right, what happens, sorry, that should just be gamma over 2, not, don't put xy because you have transformations, okay, typically, what we're looking at, right, is we have, in this case, plane strain, right? And if they want the maximum, the largest principal strain, right? We already know what, that epsilon z is equal to 0. So we only need to use 1 more circle, okay, for this particular part. Because we're interested in the largest principal strain. Where is the largest principal strain? Right there. Okay, like that. So we're usually only concerned with this one. Okay. But when we look at a question where we have to find the absolute maximum shear, strain or stress, okay? And this is maybe a little bit of a review for Tuesday because you will need to be able to calculate the absolute maximum shear stress. right? That's when you want to be careful and you want to make sure that you've got all three. Right? So if you had some type of state like this, you're going to draw another one, right? Because we know that epsilon 3, epsilon z is equal to epsilon 3 is equal to 0. And that's this point right here. This one right here, that's going to be the epsilon 2. This one right here is going to be the epsilon 1. Okay? And so we're interested in drawing the third, assuming that epsilon 1 and epsilon 2 are both greater than 0. Okay? Assuming that just because epsilon x and epsilon y are both greater than 0, that does not mean, right, because you can imagine some rotation, right, where one would go negative, okay, your epsilon 2 would go negative. But if your epsilon 1 and epsilon 2 are both greater than 0, then we have to be concerned about calculating out or drawing out the largest Morse circle. Okay? Yes?
Since you're graphing gamma over 2, does that mean like if you have your radius straight up, your radius is giving you half the
Yeah. So you're gonna calculate your radius, right? Okay, so let's calculate the radius here, or the radius here, or the radius here. Okay, and let's just say, right, the radius in this one. Okay, this is the radius over here, r for the r12, let's call it, right? That's going to be epsilon 1 minus epsilon 2 over 2. Okay, but then in this case, the gamma 1, 2 max, shall we say, right? This is confusing. The way I would do it is say, I'm going to divide it by 2. The gamma 1, 2 max divided by 2 is going to be equal to R12, right? And so that the gamma law max 1, 2 is equal to 2 R12. Okay? Good. Thank you for asking the clarifying question. Okay. Other questions? Take a couple seconds, if you haven't already, to work on, we have question 2 and 3 here, so at least take a shot at one of them. It doesn't really matter which one. Maybe the other one is a little bit easier, I don't know. You only have to think about one more circle. Question 2. Maybe number 3 is a little bit easier. Just take a couple minutes off. And then we'll get into our last and final topic. Yes. Yeah, so that's R12, that's R12, right? Those are both circles. Okay? I mean, they're both radii, right? It's a circle, so I can define the radii, horizontally. I can define it at 45 degrees. I can define it vertically. Yeah, so when you're given these, when you're given these, right, you need to be careful, right? And in this case, right, gamma xy over 2 is going to be 10, right? So when you plot that point, okay, over here, right, you're going to want to go down 10 as well. Okay, so yeah, you have to be very careful. So the vertical distance is going to be twice what is given to you. But epsilon x and epsilon y, those are going to be exact. Yeah.
Q2 does. I already forgot. I did that.
Is there a question? Okay. Do you have a question?
Sort of.
Yeah.
Not a question, it's just curious.
What'd you change? For now, for black and then for number 3, you don't really have to draw it out.
Okay, are you talking about the principal strain? Are you talking about the maximum strain? Okay, or the max, you're talking about absolute max shear or maximum
Yeah,
or the principal strain?
Absolute max shear.
Okay, absolute max
Basically
shear,
just-
yeah. So that one, in this case, right, once you figure out what epsilon 1 and epsilon 2 are, right, you gotta figure out what the radius of this circle is. And that's what this is. And then that's gonna be the absolute max shear.
Yeah.
Any other questions on
But
this?
since
We've got a few more things to go through, okay? Or one more topic. So we're gonna move on.
the shear strains are like divided.
Hopefully this has whetted your appetite if you haven't quite finished it.
It's just
Okay. So finally, and following kind of what we've been doing with our treatment of plane stress, we're going to do it with plane strain. We're going to talk about what the use of these transformations might be on a structure. Okay? And this is a little bit different because now we're discussing how you can actually experimentally characterize what the state of stress or strain in the structure is with sensors. Okay? So strain sensors allow us to measure the strain on the surface of a material. And our group has done some work in wireless strain sensing actually. We were doing this with NASA because we were interested in being able to design a strain sensor that didn't have wires going to it, that might be on the inside or the outside of a pressure vessel. Okay, and if you're going to have to, drill holes through that pressure vessel to wire to your strain sensors, that could be a little bit annoying. Okay, or maybe you've got your cabling and such that you don't want to go from one beam to another beam, right, to get to the strain sensor. So if you can address it wirelessly, that can be useful. And we were doing this looking at passive, again, it's not this, but we were looking at passive wireless sensors. So wireless sensors that you don't have to put a battery on. Okay? Now, the simplest case for a strain gauge is that it tells you what the strain is in one direction. So if we're thinking back to the good old days where we have uniaxial loading on a bar, right? And the strain, okay, is essentially axial. Okay? We can figure out what the relationship is, okay, between, say, the lateral strain and what it is, and the stress in the axial direction. Now, it turns out, okay, that you can think of a strain gauge as a wire. Okay? And does anyone remember how to think about the electrical resistance of an electrical wire? How do you guys think about electrical resistance in a wire? Like, what does your mechanical mind say? Yes. Huh? A pipe?
No, he's talking about like how you would prevent water in a circuit. And then
Yeah, that's what I was going for, yeah. Yeah, pipe constricting, okay, yes, I can understand the words. Okay, yes, it's like you're squeezing your hose, right? And if you constrict, right, that diameter, right, it's harder for the water to go through. Okay, same thing. If you make a wire, so here's the thing, if you make a wire smaller in diameter, does it have higher resistance or lower resistance? No, if I make it, well, what do you, okay, so if I make the pipe smaller, does it have a higher resistance or a lower resistance?
Yeah.
It has a higher resistance, right? It's harder to get that water from one end to the other, you have to put more pressure on it, right? It's like, think all the pressure that goes into getting fluid through a syringe needle, right? There's going to be a higher pressure there, okay? So we can relate electrically the resistivity, which is a material property, okay? And the longer the tube is, and the larger the cross-sectional area is, or the smaller the cross-sectional area is, the higher the resistance. Okay? So you can think about what is the resistance of this wire. Now it turns out, right, you can then begin to think, look, there's a wire that's going back and forth here. You see that? And if I stretch that wire out, what does Poisson ratio say? It says its diameter has to get smaller. All right, so the cross-sectional area gets smaller. What's going to happen to resistance? Up. If I stretch the wire, what happens to its length? Gets longer. So both length and the smaller cross-sectional area make the resistance higher. Okay. Now, it turns out that it's not exactly all dependent on the cross-sectional area. Okay. So truth be told, it's not. But it's a nice picture to have. Okay. It turns out that it's also dependent on the change of resistance that the material undergoes under strain as well. Okay. And the gauge factor is something that people talk about when they say this is the ratio of change in resistance divided by strain. So we can think about the gauge factor, okay, for a given sensor in terms of the amount of strain and how it's affecting a change in electrical resistance, right? So like we're mechanical engineers, but guess what? We still need to sense things, and charges are a good way to sense them still, in many cases, okay? So one strain gauge can help us understand extension in one direction. All right. But if one direction decides to split up into multiple groups, all right, we get more of a panorama of their musical capabilities. All right. And what we do sometimes is we use multiple one-directional strain gauges, okay, to be able to figure out what the state of plane stress or plane strain might be on the surface, right? As we know, a pressure vessel, cylindrical, right, in particular, has a hoop stress, hoop strain, right, and a longitudinal or axial stress and strain, okay? So we can pick different orientations of these strain gauges to each other, okay? And these are called rosettes, all right? So we get 3 directions, okay, out of this, right? And so guess what? How many parameters are we trying to measure? Sigma x, sigma y, tau xy. 3, right? Or epsilon x, epsilon y, epsilon xy. 3. 3 sensors, 3 unknowns. Okay. And they can be put in different orientations relative to each other. Okay, so the common ones, all right, are the 60-degree and 45-degree orientations. We go back to our equations, okay, for transformation. So for the rectangular rosette, that's the one with the 45s. Okay, we can figure out how epsilon A relates to epsilon x. What is epsilon A? That's the sensor A here. Okay, and guess what? It's in line with x, so that's a pretty good estimate. All right. Epsilon B, all right, that is more complicated, but it gives us a relationship between epsilon x, epsilon y, and gamma xy. And what do you know? Epsilon C is just going to be epsilon y. Okay. So we can do a little more algebra, and we can figure out what gamma xy is, right? So you just plug in epsilon x, epsilon y into this equation, rearrange things, and you take the strain measurements from these different, all 3 of the strain sensors, and you can figure out what gamma xy is. Okay? Similarly, for 60 degrees, we can use these equations, all right, to figure out what the relationship is between the strains that we measure at these different locations might be, and what epsilon x, epsilon y, and gamma xy might be. Okay? All right? And so these are the transformations. It's a little bit more complicated. Okay? And ultimately, right, we have relationships that tell us what epsilon x is, what epsilon y is, and what gamma xy is. Okay. Any questions on this? Okay. You see what we've done here, right? We're using our plane strain transformation equations with these strain gauges at different angles to then calculate out what the state of stress is, okay, in an x and y direction. Okay, so you'll get an opportunity to work on calculating out what the state of stress is, okay, given a rectangular rosette, okay, where you have an A, B, and C gauge. All right, and that covers what we've wanted to do today. Any questions? Any questions? All right. So now everyone's favorite moment.